do? It affects the y values, right? Yes, it stretches it. So let's graph y equals x squared. Remember the little quick way, 0, 0, 1, 1, 2, 4. Bada bing, bada boom, that's it. Quickest graph you ever drew? Yeah? Now, that pattern, 0, 0, 1, 1, 2, 4, what happens when it's y equals 3x squared? The y values are stretched. So 0, 0 becomes 0, 0. The y value didn't get affected. 1, 1. The height of 1 now is stretched to 3. 3 times the height. 2, 4. 4 got stretched to 12. Up off the charts. Off the charts here. There we go. Y equals 3x squared. Going back to the next one, sketch y equals 1/2 x squared. So 0, 0. 0, 0. Now look at my 1, 1. What's the 1, this height of 1 going to become? 1/2. So 1/2. 2, 4 becomes 2, 2. Do you remember what this looked like? It's wider. Yes? Wider. So in y equals 3x squared, each y value is triple the corresponding y values in y equals x squared. This is a vertical stretch. Vertical is spelled C-A-L. Factor of 3. Factor of 3. So if they said describe what happened here, you would say vertical stretch factor of 3. Okay, in y equals 1/2 x squared, each y value is half the corresponding y value in y equals x squared. This is a vertical. Okay, so now I need to, okay, so if you look at the beginning of your booklet and you look at the outcomes, they use the terms stretch and compression. So if you look at this, the blue is the normal. Do you see? I stretched it this way, and if I go this way, I'm compressing it. Okay? So we're going to talk about that a little later, actually. We're just talking vertically right now. So our movement is this way, vertically. Okay. So this is a vertical compression factor of 2, or you can say it vertical stretch factor of 1/2. This type of description will be the only description in the back of the textbook. Vertical stretch factor of 1/2. Okay, I need you to be familiar with both because they have asked on the exam using the term compression before. So it's implied compression means you're flattening it. So that means you're not having it, because if you're having a compression, you're actually stretching it, right? So again, I'll repeat, the vertical stretch, when it is a stretch, we state it that way. When it's a compression, I would still refer to it as a vertical stretch factor of 1/2. It's just easier to remember they're both stretches. But in your mind, you know it's a compression. And so if you ever have to describe it as a compression, you know the factor is actually the other way. Does that make sense? Honestly, all you have to do is remember this way. But again, it's like you have to be familiar with both terms. But you'll probably never see the rest until they ask you on the exam. Okay. Notice some of the points don't change. They're known as invariant points. Okay. So, does anybody know what example 2's graph looks like? In physics, have you seen this? This is a sine graph. You'll get familiar with that soon enough. Okay, so what's happening here? This is my f of x graph. G of x is 2f of x. So what do I have to do? I need to stretch vertically factor 2. Vertically means it's only affecting your y's. So 0, 0 would stay as 0, 0. Yes? How about this one? It looks like it's approximately 2, 1 would become 2, 2. It gets doubled, so it's going to go like this, up. Go back down to 0, 0. Actually, 4, 0. Yes? So, negative 1 gets stretched to negative 2 now. So that's the end of my stretch vertically factor of 2. The next one, again, it's affecting the y's. It's outside the function. Do you see that? So it's affecting the y's. So how do we describe this? Stretch vertically factor of 2. Whoops, I said that wrong, didn't I? Factor of a half. I could also call it what? Compression factor of 2. Very good. Okay, so same thing. It's only affecting the y. So 0 stays as 0. The height of 1 now is a half. This is why we ask questions. Okay, so then you see it's half, and then the negative 1 goes to negative a half. And let's think about this for a second. If it was compressed vertically, it got squashed. Does that look like it got squashed? Yeah. Okay. So now I have a table of values. I say that loosely. It's not really a table of values. It's a chart. Okay, we have our mapping notation. Here's my x, y. Here's the transformation, 2/3 f of x plus 2. So who can describe what happened here? Yeah, so I hear up to and then a stretch of 2/3. Okay, so here, do you remember the acronym bed mass? You need to follow bed mass. The multiply effect happens before the adding or shifting, okay? So, we take the y values, we multiply by 2/3, then we add 2. Do you see that? Okay, so x doesn't change. We have 2/3 of the y, and then we have to shift it up 2. Does everybody understand how I get the mapping notation? Okay, so negative 4, 0 is this point right here. This is why a chart's sometimes better when you start getting into multiple things happening. So all of these, the y's don't change, sorry, the x's don't change. So I'm just going to put all the x's there. Yes? Okay, so 0 gets multiplied by 2/3. What is it now? And then I add 2, I get 2. So this negative 4, 0 is now negative 4, 2. Okay, this is for all the extreme fraction people. Negative 3 times 2/3, what do we get? Okay, for all the people that can't see, it's negative 2. Negative 3 times 2/3. Do you see the 3's cancel and I'm left with negative 2? And then I have to add 2, I get 0. So at negative 2, this point now is here. Any questions there? Did I lose somebody with the fraction? Stop it right now. Nobody showed you could cross cancel and you got all the way up to grade 11. So it's great.
We did in grade 11.
You did do, and actually I know you did, Mitchell, in grade 11. There's no difference, Mitchell. You know when you're doing rationals? Mitchell, are you watching? Because I'm not doing this for my benefit, right? Okay. X, no, it's not. Shoot! What happened there?
I think you like this.
Wait, so I'm back to, I thought it's negative 2, 0. Let's go back to 0, 0. If I multiply 0 by 2/3, I get 0, and then I add 2, I get 2. So now this is going to go like that. 3. 3 times 2/3. You see you can cross cancel. What are you left with? 2. 2 plus 2 is 4. 2, 4. Okay, and then 0 gets multiplied by 2/3. 0 plus 2 is 2. So we get 4, 2. So does everybody see why the chart kind of helps a little when you have a crazy thing going on like that? Okay, so can you see visually that it got shifted up to, and visually, what is a 2/3? Is it a compression or a stretch? It's really a compression. So do you see it got flattened just a little bit? 2/3 is pretty close to 1, which a multiplier of 1 doesn't do anything, right? 2/3 just squashed it a little bit and then shifted it up, right? Okay, a number in front of the variable inside the function, this is the new stuff now, causes a horizontal stretch or compression. So now we're going to go back to what we know, which is a parabola. Y equals x squared. Remember that fast way? 0, 0, 1, 1, 2, 4. Bada bing, bada boom, we're done, right? That fast. So now what we're going to do is we're going to use this function machine. And I know everybody knows that you could just multiply this out and get y equals 4x squared. Okay, you know what it's supposed to look like. It looks like a skinnier parabola. We're not going to do it that way. We're going to do it as a horizontal stretch or compression because we're going to affect the input of the squaring function. So what happens here, does everybody see the y is the same? Y is y, yes? What I'm changing here is I'm changing the inside of the function, what's going in. So the inside of the function, if I take something like 2 as the input, it's actually doubling. But I still want the same output. So if I double it and then square it, I will not get the same output. Does everybody understand that? So what I have to do is I need to compensate the input by undoing that doubling effect and halving it. So this is why my x goes from 2 to 1. And guess what happens when I plug 1 in? 2 times 1 is 2. 2 squared is 4. Does everybody see I have the same output? It's kind of like this back in the day when we did the f of x plus minus 3. And you kind of said, or you just memorize, you know it goes to right 3. The reason why is you want the same output, and if your x got subtracted 3 when it went in, you have to undo that by actually shifting it to the right so you still get that same output over there. So that's why this is a shift to the right, because you're affecting the input, not the output. Okay, so same thing goes here. We're changing the input, so we got to compensate it. So the 1, I got to compensate it and make it 1/2. So when I plug it into the squaring machine, 1/2 times 2 is 1. 1 squared is 1. Do you see it's the same? 0, 0. Negative 1/2, 1. And then this still becomes the same 4. So let's graph this, and you can see 1, 4 is there. 1/2, 1 is there. 0, 0, negative 1/2, and then there. So do you see it is what you expected it to be, skinnier than the normal parabola. But the way you should be looking at this is this 2x is actually pushing it to the middle, compressing it. We're not looking at it this way, we're looking at it this way this time, that it's actually getting compressed. Okay? So, x value is half the corresponding x value in y equals x squared. This is a horizontal compression factor of 2. How else would I write this? Or a horizontal stretch factor of, what is it? A half, yes. And again, this would be the answer in the back of the textbook, horizontal stretch factor of a half. So what would happen if I make the x values a half the amount? How would I have to compensate it to get the same output? I would have to times it by 2. So let's try that. Again, back in the day, this would be the same thing as squaring it. Y equals 1/4 x squared. And you remember from grade 11 that that would be a wider parabola, right? So if I take this one and now I'm going to double the x, what does 0, 0 become? Still 0, 0. What does 1, 1 become? I'm sorry? What would 1, 1 become? No. This is affecting the x's now, right? No, don't look at that. Look at this. No, I still haven't heard the right answer. Huh? 2 what? 1, 1 would become 2, 1. I'm doubling the x, just like Usain said, right? Okay, so what would 2, 4 become? What would 2, 4 become? 4, 4. You see? Wide. This is now this. This is now the mirror, right? Wide. Do you see that? This is y equals 1/2 x the whole thing squared. This is y equals bracket 2x the whole thing squared. Do you see that? Okay. In y equals 1/2 x the whole thing squared, each x value is double the corresponding x value in y equals x squared. This is called a horizontal stretch factor of 2. Name the invariant points for the above examples. The only one would be 0, 0, because 0 and a multiplier would always be 0. Okay, this is a little bit different one. This is now, here's the two graphs. You need to come up with the equation. So, just because it's hard to tell, g of x is the skinny one and f of x is the bolder one, okay? So, I want to know what happens to f of x to get g of x. So f of x is this thick one here, and g of x is now like that. So what happens? What did I do to f of x? Huh? Compressed. I squished it. Did everybody see I squished it? Yeah? Okay. How much did I squish it by? I hear 2. I hear 3. The correct answer is, oh, now 4? Is that what I hear? No. The correct answer is 3. So look. You can't really look at this point here because that point didn't move. If I multiply an x value of 0, it's still going to be the same spot. However, this x spot here is at 3. Where is that when I squished it? It went all the way to 1. It didn't move to 1 left. It got squashed to 1. Same with this one over here. It moved to that one. So it's a third the amount now. So how would I write that? Okay, no, I mean like as an actual equation. So I'm going to have something f of x. What's going to be inside there? It's going to be 3x. Okay, why is it 3x? Because we just said it was a third the amount. Yeah, right. Okay, now look at the other way. We're starting with f of x and we're going to g of x. Sorry, I said that wrong. We're starting with g of x and we're going to f of x. So this is going to be g of what? G of what? 1 over 3x. You could also write it as g of x over 3. You're dividing by 3. So any invariant points here? For example, 5. The only invariant point was this one here. Do you see that? Some might argue, isn't this one right here an invariant point? No, because that actually moved. That goes to there, right? Or the other way around. So anyways, it's only 0, 2 is the invariant point. So this is kind of what we were talking about. A stretch factor of 1 over a is the same as a compression of a. So it's a reciprocal factor going on here. Big words.